Hello, this is John Purcell from quantumlifetime.com. In this tutorial we're going to look at intensity and we're going to look at Malus's law of a light wave. Let's imagine a wave of light that's shooting off in this direction, let's say. Now this ray of light may transfer energy, or we could think of it as containing energy. And we could ask how much energy passes a particular point in unit time. And in fact, since the light wave it doesn't take up the whole universe, it has kind of a finite cross section. We really want to talk about the energy per unit area, the energy that passes through a unit area per unit time of the light wave. And we call that the intensity of the light wave. So intensity, which is often denoted by a capital letter I, that's intensity equals energy per unit area per unit time. And because power is defined as energy per unit time, that's therefore equal to the power, the rate of energy transfer per unit area. And if you let light, for example, visible light fall on a black surface that absorbs most of it, then intensity is going to be a measure of how hot that surface tends to get, if you assume kind of 100% efficiency and that kind of thing. So intensity is a measure of the energy per unit area, per unit time that light wave could transfer to a surface, or you could think of it as a measure of the energy that's passing through a unit area that's enveloped in that light wave per unit time. Now we've seen that the energy of a light wave is proportional to its electric field strength. And so we can write that intensity, therefore, is going to be proportional to the square of its electric field strength. So the intensity is going to be proportional to the square of the electric field strength of a light wave. And let's imagine that we've got a force. It could be wind, for example, that's blowing in this direction. And let's imagine that we've got an object that's being affected by that force, but it's constrained to move in this direction. I'll call this F0 and I'll call this F1. So this could be wind, and this could be a ball that's being blown along by the wind, but the ball is attached to a track, let's say, that runs in this direction. We know that the force F1 that ball experiences in this direction, if this is an angle theta, F1 is going to be equal to F0 cos theta. This is kind of basic physics. And similarly, if we have light that's polarized in this direction, let's say, and it passes through a polarizer that's at some angle to the electric field of the light, then we can say that the electric field that succeeds in getting through this polarizer, so we have to imagine light kind of passing through this polarizer, the electric field strength that gets through, let's call it E1 and let's call this E0. E1 will be equal to E0 cos theta, and therefore the intensity, which is proportional to the square of the electric field strength, I, is going to equal the original intensity, is energy per unit time, times cos squared theta, because the intensity is not directly proportional to the electric field strength. We have to square it to get we have to square this to get the resulting intensity, and we have to square this to get this. So this is called Malus's law, and it says that when light passes through a polarizer, the resulting intensity is the original intensity times the cosine squared of theta, where theta is the angle between the original polarization angle of the polarized light and the polarization angle of the polarizer. And we're going to go on to look at this. We're going to go on to look at how this affects light that passes through multiple polarizers, and then we're going to look at how we'd imagine photons to be therefore affected as they pass through polarizers. So join me again next time. Don't forget you can find more tutorials as well as a podcast on consciousness and quantum physics, kind of more metaphysical, on quantumlifetime.com. And until next time, keep it real.